Thank you for the introduction. My name is Tauhid Shekari, and today I'm going to present my paper. This is a joint work with my colleagues at the School of Electrical and Computer Engineering at Georgia Tech. So, let's start with a brief background on the power grid structure. Generally, power grid has three main sectors: generation, transmission, and distribution. In the generation section, most of the required energy by the customers are generated by large power plant like nuclear power plant. The transmission lines are responsible to transmit electric energy over long distances. And finally, distribution systems are responsible for distributing energy to the end users in a small geographical area. But these three sections have different voltage levels, and we use a piece of equipment called power transformer to change the voltage level in these three sections. And these power transformers are located in substations, and they are controlled by the control center. So here in this slide, you can see the general layout of a power substation. It has two power transformers with the same application that I mentioned before, two circuit breakers, and they are simply switches that can connect or disconnect the different components like power transformers to the power lines, and a communication box which includes the measurement devices which are measuring the current and voltage of the power circuits, and also protective relays, which are measuring the voltage and current to detect any kind of faults in the system to isolate the faulty area. Also, there is another device inside the communication box, which is called remote terminal unit, or RTU. And these remote terminal units are responsible for polling measurements from the power substation in every few seconds and report them to the control center, and also implement the control actions coming from the control center in the substation. So generally, we have similar structure like this in the power grid. The control center monitors multiple substations across the grid. It pulls the measurements every few seconds. It runs the computations on those measurements, and it sends the control actions to the substation RTUs to be implemented in each substation. The power grid attacks actually basically started from Ukrainian power grid attack, which happened on December 2015. And during this attack, attackers got access to the substation RTUs. They opened circuit breakers to simply cut the power to the customers. They could affect more than 30 substations and 230,000 residents for more than 6 hours. And also, they simultaneously launched distributed denial of service attack on the call centers so that the power companies couldn't hear the complaints for 6 hours. So they basically didn't have clue what's going on in their grid. In this work, we focused on power substations, but what are our motivations? The first reason is that power substations are the main target for the attackers. They offer a very large attack surface. For example, in the United States, we have more than 70,000 remotely operated substations, and we recorded more than 2 million attacks on these substations on a daily basis. Most of the existing mechanisms and solutions to secure the power system substations are based on traditional IT practices like patching more frequently and training the personnel more frequently and more effectively. And there are also some other effective methods which proposed recently. They are based on the SCADA network traffic. They use machine learning methods to extract the signatures of the malicious packets to detect attacks. And these works are effective when there are attacks like network scanning or password guessing. But what if the SCADA system has been compromised totally? And also, they are vulnerable still to zero-day vulnerabilities. So the general idea of our solution is to deploy low-frequency antenna which measures the electromagnetic emissions of power circuits within the substation, and it is robust against the replay and spoofing attacks. So basically, we place our antenna next to the power circuit, let's say 10 feet, 20 feet away, and it measures the electromagnetic signal, which has two main components. The first component is coming from the circuit current, and the second one is coming from the lightning strokes happened in a very long distance. From the first component, we can extract the SCADA network traffic attributes and check the accuracy of the network traffic to see whether it's been compromised or not. And from the next attribute, we can use it for the signal authentication. And I will explain how. For the signal authentication, we use lightning because if every lightning that is happening, it causes a huge current, and this huge current radiates a very large and strong electromagnetic signal. It can travel long distances, like 2,000, 3,000 kilometers away. It is a totally random phenomenon. It cannot be predictable. And it happens roughly 3 million times per day, or 40 times per second. So it's enough to authenticate our signal. And if the attacker wants to physically manipulate this, physically generates a signal similar to this, he can do that with only nuclear explosion. And it travels at the speed of light, so it's very fast. We don't need to wait too much time to authenticate our signal. So let's go into the detail of this. So there is a lightning database, which is called National Lightning Detection Network. It actually gives you the real-time access to the lightnings happening around the world. It gives you 3 attributes: lightning current, location, and occurrence time. So by looking at this lightning database and by detection of the lightning impulses at the location of the substation, you can calculate the expected arrival time of the lightnings in the location of the substation, and you can check the integrity of the signal. For example, here it shows the 3 different electromagnetic signals captured from 3 different locations. As you can see, the lightning signature in these 3 locations are the same, but there is a slightly time shifting, which is coming from their different distances from the lightning location. Once we authenticated our input signal, sensor signal, we can start our analysis on the SCADA network. We want to check the integrity of the SCADA network. So we have the electromagnetic emissions from the power circuit. We extracted direct mathematical equations to reconstruct the circuit current. And there are 2 attributes which are useful here. The first one is harmonic content, especially the first harmonic 60 Hz, and the second one is the fundamental frequency. And these 2 values are basically reported to the control center as the measurements. And also, control actions are affecting these measurements. So if any of these control actions like circuit breaker opening, closing, transformer tap changing happens in the substation, they will affect the current of the circuit, and we can detect them. So we can successfully extract the measurements and control actions from our signal and compare them with the network traffic to check its integrity. So here it shows the overview of our scheme. Our intrusion detection system has 4 inputs: local magnetic field coming from our antenna, lightning signals coming from nearby substations, lightning database, and the network traffic. The first 3 attributes are used for authenticating the measured signal, and network traffic and measured local antenna signal is used for checking the integrity of the network traffic. We considered 4 levels of attackers with different defense mechanisms. The first attacker can attack and compromise the network traffic totally. In this case, from the second method, we can successfully see if there is an inconsistency. The attacker might try to even compromise our own signal, and we can check the integrity of our signal with the lightning database and the lightning signals coming from nearby substations. The attacker even might try to go one layer deeper and compromise the lightning database. But again, because of the presence of signals coming from other receivers, we can still authenticate our signal. And the attacker, if goes one layer deeper and tries to compromise everything, if the attacker can compromise more than half of the receivers we deployed, he can circumvent our method. But this requires a lot of effort to compromise basically N, for example, air-gapped systems, which is very hard. So we validated our method with both experimental and simulation results. Here is our measurement setup. We designed low-frequency antenna. We had preamplifier, awesome receiver, and computer. We captured the experimental results from three substations. One is located in Atlanta, 2 others located in Eastern Shore of Maryland. And we used Power System Simulator and MATLAB for simulation. The first attack we simulated, we used experimental data for the lightnings, and we checked the lightning authentication scheme. We fed our algorithm with both legitimate and spoofed data, and we could capture 99.99% true positive and true negative rates, which is great. And also, we will look at the circuit breaker malicious switching. We had experimental results for this, and there are a couple of other attacks. You can find them in the paper. We don't have time for them today. And so I should mention that basically every attack that can affect the circuit current, we can detect that with our algorithm. So let's take a look at the circuit breaker malicious switching. So first, we have the SCADA network traffic. We can see that from this network traffic, we can see that circuit breaker opening happens at 11:09:35. And then we have magnetic field signal measurement, and we have 2 attributes to detect circuit breaker opening. The first one is the presence of 3 consecutive impulses, which is prevalent from this figure. And also, if we extract the first harmonic of this signal, we should see the decrease in the first harmonic signal, which is the case. If we see increase in the signal and also 3 impulses, it's a sign of circuit breaker closing. And in this case, because this was a legitimate circuit breaker opening, the time obtained from the SCADA network traffic and the measured magnetic field signal are exactly the same. But in the case of attack, they will be different. So as conclusions, we proposed air-gapped physical signal-based distributed intrusion detection system. And our developed sensor is robust against spoofing and replay attacks. And we use natural phenomenon lightning for authentication. And our proposed method is able to detect cyber attacks on power substations with high accuracy. But we also have some weaknesses. The first one, we only use the time of the lightning in authentication method, but we can use the intensity and shape of the signal, which makes it even harder for the attacker to attack our system. We noticed that if we deploy our receiver even far away from the substation, like 200 kilometers away, we can still detect some of that activities in the substations. And also, we assume that we have balanced 3-phase systems in the power circuits, but we're going to study and formulate the unbalanced systems in our future work. And finally, we assume that there is 1 receiver per power circuit in the current method, but we noticed that we can reduce the number of receivers to fully protect the substation. So in our future work, we will study the minimum number of receivers within the substation and their optimum location. Thank you very much, and I'm here for the questions.
We have lots of time questions.
Hi, I'm Niels from CISPA. I have a question on essentially your attacker model. Maybe I missed it a little bit. So you assume that the attacker is aware of this countermeasure being deployed as well? Or
I can't hear you, sorry.
Sorry, okay. I'm Niels Stippenhau from CISPA. I have a question on essentially your assumed attacker model.
Okay.
You assume that the attacker is aware of this defense mechanism being deployed or not? So let's assume the attacker is somehow able to spoof the sensor values of your magnetic field sensors.
Yeah, if the attacker spoofs our sensors data, so actually the lightning, we extract the lightning impulses from our sensors data and we compare it with the expected lightnings coming from the other databases like lightning database and the other receivers. So it acts like a watermark. The attacker can't even change our signal.
Yeah, I get that part. So there's actually another question that I have afterwards on this. But so what prevents the attacker from just incorporating these kind of lightning-induced signals into the spoof signal as well?
So it's very hard for the attacker to extract them and reconstruct a legitimate, actually magnetic field signal in real time. So it takes them, it's computationally somehow intensive to do it in near real time.
Okay, so the assumption is that if I have access over the actual sensor and I get the real measurements, I can't just deduct the influence of the actual power lines from that signal to obtain kind of lightning-induced components?
So we extract two attributes. We first extract the lightning signals to authenticate our measured signal, and once we make sure that, okay, our signal integrity is correct, we can take a look at the other attributes like the harmonic content and the fundamental frequency. And those two attributes helps us to validate the network traffic.
Yeah, okay, maybe we can take this offline as well. The question is more like how powerful is the attacker here? Sorry.
Can we take a question offline? There are people waiting.
Yes. So one more comment. The authentication is kind of offline, yeah, because it takes a while to get this data then from the Lightning database. So the authentication is not
near real time. It's not offline.
Okay, thank you.
You're welcome.
Hi, I'm Daniele from SUTD. I didn't really get the explanation about this authentication protocol based on Lightning. Can you please elaborate a bit more about this scheme? Because it looks like there is not a real connection between Lightning and the SCADA system, right? So in principle, I can also use your Lightning authentication scheme to authenticate other stuff.
Yeah, you can use the same concept in other applications. Basically, if you have any other applications that you can capture the electromagnetic field from outdoor, you can use the same authentication method to authenticate your signal. It's an independent method. It doesn't have anything to do with the power
but I guess
grids.
it depends on the position of the lighting, right? How can you use lighting to authenticate something, right?
So let's say we have three signals here coming. Actually, we captured these three signals in three different locations from here, and there is the signature is the same, right? But only there is a difference between the timing, and this timing difference coming from, for example, if a lightning happens here, it takes different times to reach out to these three locations. And if you have access to one of them, you can authenticate these two, the other two ones.
Yeah, but you don't have an amount of lighting in the same position that is close to your SCADA system during the whole day. Maybe you have 3 lightning per day in that position, right? You might have a lightning somewhere else.
Yeah, it doesn't matter because it can travel 1,000 kilometers. So in the continental USA, we could actually capture roughly 40 lightnings per second. So it's a lot of, for example, here in 1 second, you can see how many do we have. It's more than, 40, 60.
Okay, thanks.
One quick question.
So, Michalis from NGO Abu Dhabi. So I wanted to ask about the practicality of the authentication method, right? Because if you say it's near real time, the lightning has to be captured, recorded, and then transmitted to you, and then you have to receive it, and then check, and we're talking about 0.05 seconds, right? So is there a practical implementation, practical communication channel that you can implement?
Yeah, so we actually validated this with near real-time measurements. We had access to the Lightning database. It's under a license, an agreement with Georgia Tech and a company called
What was the
Wisely.
communication? Was it over Wi-Fi, wireless? Was it like antennas communicating? How do you get the data from the main database to your receiver?
It was
near the
available. So the way that we checked that was actually we had access to the Lightning database in an online server. So we just had access to that with internet.
So internet speed is enough for this.
Yeah. It's actually, it doesn't need any, any high bandwidth to actually communicate these things because it has 3 attributes and very, very low bandwidth to communication.
Okay, thank you.